So today we'll be presenting an evaluation of Dijkstra's algorithm applied to our application Singapore MRT Route Finder. Dijkstra's algorithm was developed by H.Q. Dijkstra in 1956. It solves the single-source shortest path problem on weighted graphs with non-negative edges, and today it powers everything from Google Maps to network routing protocols. For this assignment, our goal was to evaluate how effectively AI chatbots explain and reason about Dijkstra's. We posed 15 structured questions to the chatbots. As a practical component, we also built a Singapore MRT Route Finder, a browser-based app that applies Dijkstra's across all 6 MRT lines. For methodology, we used two chatbots, Claude by Anthropic and ChatGPT by OpenAI. Each has distinct strengths. Claude tends towards contextual reasoning and nuanced limitations, while ChatGPT excels at structured formatting and step-by-step code explanations. We evaluated both chatbots across 4 criteria from the assignment brief: accuracy, completeness, clarity, and relevance. We also added a fifth criterion, contextual reasoning, to capture how well each chatbot link is answers back to our MRT scenario specifically.
How does the extra algorithm work? Let's walk through it step by step. It starts with initialization. We set every node's distance to infinity, except for our starting station, which gets a distance of 0. That station is then added to a priority queue. Next, we extract the minimum. We pop the node with the smallest known distance out of the queue. This is the greedy part of the algorithm. We always commit to the closest unvisited node first. Then comes relaxing edges. For each unvisited neighbor of our current node, we check, is the path through this node shorter than what we already know? If yes, we update the distance. After that, we mark the node as visited. Once a node is finalized, its shortest path is confirmed and we never revisit it. This is also why the algorithm breaks down with negative weights. A finalized node can't be reopened. We then repeat steps 2 through 4 until we either reach our destination or exhausted all reachable nodes. Finally, we reconstruct the path by tracing back through a previous node map that we built along the way, giving us the full shortest route from the source to destination. In our MRT route finder, these exact 6 steps are what run under the hood every time you click Find Shortest Route. Now that we know how the algorithm works, let's talk about how efficient it is, because that depends heavily on the data structure you use to manage priority queue. The simplest approach is plain array. You can scan all nodes to find the minimum each time, giving you O of V squared time. It only uses O of V space and works well for small or dense graph, but it doesn't scale. The standard choice in practice is binary heap. This brings time complexity down to O of V plus E log V by using efficient heap operations. Space goes up to O of V plus E to store the edges, but this is the implementation used in our MRT application and in most real-world systems. The theoretical optimum is the Fibonacci heap, which achieves O of E plus V log V by supporting amortized O of 1 decrease key operations. However, as both Claude and GPT pointed out in our evaluation, the high constant factors and implementation complexity means it's rarely used outside of academic settings. In Python specifically, which we use to validate our logic, the heap queue modules use a technique called lazy deletion. As a practical workaround to decrease key, it reinserts nodes with updated priorities and simply skip stale entries when they are popped. This achieves similar efficiency to binary heap without needing explicit key updates. For our MRT networks, which is a sparse graph with around 130 stations and roughly 150 edges, the binary heap implementation is more than sufficient to run near instantly.
I'm Chu Chin and I will be discussing on the 4 data structures that come together for the Dijkstra algorithm to work. So firstly, it is the min heaps priority queue, which always selects the station with the smallest current distance. And it is important because Dijkstra is a greedy algorithm. So at every step, it expands the closest station first. Next is the distance array, in which it stores the shortest distance, known distance from a starting station to every other station. So as the algorithm runs, these values are being updated constantly whenever a shorter path has been found. So next, it will be the visited set, in which ensures that once a shorter path has been found, it will the shortest one possible, it will not be processed again. So this is just to help the efficiency of the algorithm and ensure that it avoids unnecessary computation. And finally, we have the previous node map, which keeps track of how a station is being reached. So this allows the algorithm to reconstruct the final route. So with these 4 data structures working together, it makes the Dijkstra algorithm works. So now I'll be discussing on the limitations of the described algorithm. So firstly, it does not work with negative weights. Once a node is finalized, the algorithm will just assume that this is the shortest path and it is fixed. So in such cases, algorithm like Bellman-Ford would be more suitable. Secondly, it assumes a static graph. So if travel time changes due to, for example, conditions like peak hour congestion or delays, the algorithm will need to be rerun again to reflect these updated conditions. So thirdly, it is directionally inefficient as Discra explores all possible paths rather than focusing directly towards the destination itself, which can lead to a lot of unnecessary computation. So here on the right, we compare Discra with other algorithms. So BFS is a very fast algorithm, but it only works for unweighted graphs, so it cannot handle MRT systems where transfers have different costs. A star can be faster for larger networks because it uses a heuristic to guide the search, but it requires additional design and it is not necessary for a relatively smaller MRT network. So overall, Discra is still the most suitable choice here because it handles weighted graphs effectively and guarantees the shortest path without requiring extra assumptions.
Now I'll be talking about the chatbot evaluation results. Both chatbots scored highly with distinct strength across the criteria. So in terms of accuracy, it was 100%. Both AI tools were 100% accurate. There were no factual errors in any of the 10 questions, and all technical steps were correct. In terms of completeness, Claude provided more details by identifying 4 limitations compared to ChatGPT's, which is only 1. It also named specific advanced methods, such as bidirectional Dijkstra. In terms of clarity, ChatGPT was easier to follow because it used clear number lists and helpful code comments. Claude's writing was detailed but difficult to read. In terms of contextual relevance, Claude did a better job of applying its answers to the MRT scenario, such as explaining how to model interchange stations. Yeah, ChatGPT's answers were too general. This is our Singapore MRT Route Finder, a browser-based app with no external dependencies, just HTML and JavaScript. Stations are grouped by MRT line in the dropdown, so it mirrors how commuter actually thinks about the network. So for example, Jurong East to Punggol. As you can see the step-by-step route, the line color badges, and the transfer station highlighted there. It shows the number of stops, number of transfer, and an estimated travel time. Travel time is estimated using an average of 2.5 minutes per stop. In reality, this varies, but it gives a reasonable approximation for a transit network of this scale. All of this is powered by Dijkstra running live in the browser, finding the shortest path across the full 6-line network instantly.
So the practical component brings all of this together. The application models the full Singapore NLT network as a weighted graph with an adjacency list covering the north-south, east-west, Circle Line, Northeast Line, Downtown Line, and the Thomson East Coast lines. So the Dijkstra core is implemented in JavaScript using a sort-based mean priority queue, a visited set to prevent reprocessing, and a previous node map for each path reconstruction. So the user interface provides two drop-downs grouped by MRT lines. Once you click Find Shortest Route, the algorithm runs and displays a step-by-step route cut showing station names with line color badges, transfer indicators, and a full travel time estimate. So that formula is stops times 2.5 minutes, followed by plus transfers times 5 minutes, and plus a 3-minute boarding buffer. So as for Dijkstra specifically, all MRT edge weights are non-negative. The network is finite and static during a query, and an adjacency list is efficient for sparse transit graphs. The algorithm guarantees the globally optimal fewest stop route each time. So to summarize everything, first, Dijkstra's algorithm with a binary heap delivers OV plus E log V efficiency and remains the industry standard for real-world routing problems. Secondly, both AI chatbots prove highly accurate and genuinely useful as learning tools. Claude excelled in contextual reasoning, and for ChatGPT, it excelled in structured step-by-step explanations. When used together, they complement each other very well. And lastly, the MRT route finder demonstrates that Dijkstra translates effectively to a real transit network. delivering the correct optimal routes across all 6 lines.